Okay, good morning, everyone. Welcome to day 2 of um, economic engineering and day 2 of market design. So let's get started. It seems like everything, so we recorded the lecture yesterday and it seems like that all worked well and it should actually be uploaded. So if you wanted to review anything from the lecture, then you certainly could. We're again recording today and let's see. So if you could open up your participant window and your chat box, we're going to use the chat feature today. So if you could just open those up and have those windows open, hopefully that works for you. You've got enough space on your screen. That would be great. Good. So last class we finished talking about the standard auctions of a single item, first price, second price, English and Dutch auctions. And today, actually, where we ended up was we just looked at first the English auction, which is now primarily implemented as a ascending clock auction in most of the modern online auctions, and the second price auction. And we analyzed the behavior in both and found that it was a dominant strategy to bid up to your value in both of those auction formats. And that was very nice because we get efficiency, we have very simple bidding strategy. And I should say the second price auction, well, the ascending clock is especially straightforward for the bidders. The dominant strategy is obvious. So in the lab, almost everyone follows the dominant strategy, bidding up to their value. And whereas in the second price, it can be a little tricky for some people. And so most everybody figures out that they should be bidding their value, but sometimes there's some folks that bid above their value. That's sort of the typical lab deviation for those inexperienced parties, but they basically, both have very strong incentives. One super nice thing, in addition to the dominant strategy and efficiency of the ascending clock auction, is it also is a no regret auction. So you don't, there's no risk that you'll end up being in a position where you regret what happened. I mean, certainly if you're a loser, you're disappointed that you lost, but you know why you lost. You lost because somebody bid higher, stayed in longer than you, and paid a price that you were unwilling to pay. So yes, you're disappointed, but you don't have regret in any action that you took. And that's not going to be the case for the next auctions that we look at. So now we're going to look at the first price auction, which is probably the simplest of the auctions because it just, you collect the bids, you open them up, whichever one turns out to be the highest, that's the winning bidder. And what price do they pay? They pay the price they bid. So it's very intuitive to everyone. Everyone's familiar with it. It seems fair. In fact, sometimes it's hard to explain to people the second price auction that, it's like, well, if somebody offered $100, why didn't you, and that was the highest bid, why don't you charge them $100? That's what they bid. Why go down to 90 just because that was the second highest? And you have to go through and explain, well, we do it because of incentives. We want it to be a dominant strategy for them to true value. And that's the reason. So, nonetheless, first price is, first price is very simple, but the strategy is complicated. So very simple rules, but complex strategy. And that's a definite disadvantage. And it's a good example that when we talk about simplicity, we want to recognize that it's not the simplicity of the rules. The first price auction has the simplest rule set. People submit a bid, we open the bids, highest bid wins, pays their bid. Okay, just a few words, I've explained all the rules of the first price auction. So super simple. But the strategy is complex. Whereas if I have, explain the second price, the rules are a little bit more complicated, but the strategy is very easy. And so I actually would view the second price and the English auction as easier, simpler auctions because I care about the challenges that the participants might have in participating. Now, one of the things with the first price auction is you are put in a position where you almost surely want to shade your bid. And that's because you want to make some money from the transaction. And so if you have a value of 100, you don't want to bid 100, you want to bid something less than that. And the question that you face is, how much should I shade my bid? The more I shade my bid, the lower the probability that I'll win, but the better the terms of trade, the more money I make, conditional on winning. And so in the first price auction, you're trading off those two factors, probability of win and profit conditional on winning. And you essentially want to balance those two. And that's what the bidder does when they solve the differential equations necessary to determine their optimal bid shading. So one way to intuitively think about it is, ideally what you would do is you would just outbid the second highest. Which if we had full information, it would actually, so we knew what everyone's value was, then it would be pretty easy. I would know that the second highest value is $90. And so I would know that they're not going to bid. They know that my value is 100, but they would be very reluctant to bid above 90. They're not going to bid below 90 because they know that I'm going to be bidding something higher. And so I would bid, 90 plus a little bit and end up winning with that. And that would be a really good outcome. The problem is in real auctions, you don't know what everybody's values are. And so you're having to solve this problem with uncertainty. And that is so, but intuitively what you're trying to do is bid the expected value of the second highest. Conditional on winning. And that is, especially if you're in a situation where you're risk neutral and we have symmetry, then that's definitely what you want to do. But if we have asymmetry or there's risk aversion will cause you to want to bid a bit more aggressively. And asymmetry will distort your bids as well. Okay, so what happens? Well, if we're in this symmetric risk neutral case, then things are actually still pretty nice with the first price auction in a single item. Because we're all going to be shading our bid. We're going to all be shading in the same way, bidding the expected second highest value, conditional on winning. And as a result, the guy with the highest value is going to win, and they're going to pay the expected value of the second highest. So which is the same as the second price and the English auction in one sense, that is the high bidder wins. But notice that the pricing is different. Now the price is the expected value of the second highest as opposed to the actual ex post second highest. And as a result, the prices differ in realization, ex post, but they're the same in expectation. So we're going to actually get the exact same revenue in the first price and the second price and the English auction in expectation, but the outcomes are not identical. It's very important to remember that. The first price auction, because the price is the expectation of the second highest, is going to be there'll be less price variation, so less price volatility in the first price auction. That's an important distinction. And another important distinction is this is an environment where we do have ex post regret. You put in your bids and let's say I bid the expected second highest, which is 85, and that turns out to be the highest bid. So I win at $85. And then this guy that has a value of $90, he's saying, oh, geez, I shaded my bid down to 75, but I sure wish I could have bid $86 and made money because my value is 90. So, I regret what I did. I'm kind of upset about this outcome. And that's one of the issues with the first price auction that causes most market participants to favor the English auction and the second price auction. They like the simplicity of the bid strategy, and they like the fact that it doesn't involve any regret. So that's for, because basically behaviorally people don't like regret, which isn't that surprising. Okay, so now let's turn to the Dutch auction. Now the Dutch auction, you'll recall, we're starting at a very high price. Nobody wants it at such a high price, and we're going to reduce the price. And as we reduce the price, people have to start thinking about whether or not to accept. If my value is 100, of course I don't accept a price of 105. I'm going to wait till the price falls to at least my value. But when it gets to 100, I don't just say, oh, I'll take it, because that would be a very bad outcome for me. It's worth 100 and I spent 100. I got no profit at all. So I want to make some money. So instead, what I'm going to do is just wait. I'm going to just hang in there, and the price falls, $99. Like, oh boy, this is great. 98, 97, excellent. I'm making more and more money. This is wonderful. And then it gets down to $91, and I'm starting to sweat because I see all these other bidders in the room, and whoever raises their hand first is going to get the goods. So it gets to $90, and I raise my hand, and boom, I get it. So I was lucky, but boy, I would have been upset if it gets to 90 and then it goes to I just keep waiting. $89, and then Mark raises his hand and he gets it, and then I'm really annoyed because I would have profited from winning at $90, and I let it slide down to 89, and Mark jumped in. So that is the dynamics of the Dutch auction. And in a simple world where we're, say, in separate booths and you can't see our expressions or whether we're sweating, then it's strategically equivalent to the first price auction. The trade-off is absolutely the same. I am simply going to wait and pick the point where I say I'll take it. And that is I'm trading off the probability of winning with the gains from trade, conditional on winning. And which is exactly what I did in the first price auction. So it's identical and the strategy is identical. Now, there is a distinction, just the way second price is not identical to the English or ascending clock auction. There is that distinction that in the dynamic auction, the element of strategy becomes more and more obvious because the decision maker, the bidder, is faced with a very simple decision, so the same simple decision again and again and again. So they're really, you know, in the English auction, it's just crystal clear that they should bid up to their value. In the Dutch auction, the trade-off, they might not even be thinking about the trade-off until it gets to below $100. And then they start to realize, okay, I like this. You know, that's, you know, now it's profitable. We're at 99. It's profitable for me, but I'm just going to wait a little bit longer. I think I can get a better price. I don't think anybody else is going to take it. And so the dynamics actually helps them make better decisions. But that's not why the Dutch auction is used. The Dutch auction is used because it is fast. And so the clock can move very quickly, and because all the participants are in the room, they all have a button that they can press at any second, and the communication is extremely simple. There's no opening of bids and sorting the bids from highest to lowest. There is just waiting until somebody presses the button or raises their hand, and if you watch these things for real, you know, in the Dutch auctions in the Netherlands for flowers, then they actually have a button that they press. So it's all electronic, and the flowers just roll by. And so it's this like continuous process for pricing, because it needs to be very fast because these flowers are not getting better as time goes by. And the other place where it's super fast is fish markets, which are fun to visit. And in the fish market, it's not electronic. The stakes tend to be very low, you know, aside from, you know, like the tuna auctions in Japan or something, but your typical fish market is fairly low stakes, so they can't support electronics. There is the auctioneer that's there, and you know, bucket of fish is presented, and the group of bidders is just, you know, looking over the bucket, and they're raising the price, and there's no buttons to press. There's no raising of hands. I'll take it. It's just little things, you know, they'll just like make some little indication, and okay, you got it, next one. And it's extremely quick. And sometimes they'll actually have disagreements because, you know, the guy just had an itch on his nose or something, and it's taken as I'll take it. But that's how quick it is and how little information needs to be communicated. So that's a important distinction, the reason the Dutch auction is still alive and well, one reason. But of course, the outcome is identical to the first price auction. In expectation, in the symmetric case, the price is the expected second price, and the highest valuer wins the item in this symmetric risk-neutral case. And as a result, the revenues are going to be the same as in the first price auction, the expected revenues. And in fact, those expected revenues are going to be exactly equal to what we get in the second price auction or the English auction. So all four of the standard auctions yield the exact same revenue in this very simple case of a single item, risk neutral bidders, symmetry. And that's the famous revenue equivalence theorem. All the standard auction protocols in fact, any protocol in which the highest bidder wins, the highest valuer wins, and the bidders with lower value, the lowest possible value make zero, lead to the same expected revenue for the seller. And that's true of all the standard auction forms in the simplest case. And so they all yield the same revenues. But we need some very strong assumptions. We need to assume that it's a single item. We need to assume that the bidders are risk neutral. We need to assume independence. The bidders' values are private information and statistically independent from one another. We need symmetry. All the bidders are ex ante, have their value drawn from the same probability distribution. None of these assumptions hold in practice. And yet the revenue equivalence theorem is still incredibly useful in guiding our intuition about what's a good design in a particular circumstance and what the implications are for revenues. And so there's lots of very powerful results that make use of the revenue equivalence theorem methodology. So it's a good example that even though the assumptions of a theorem might not generally apply, which is typically the case, the theory can still be very powerful in improving our intuition about how things work. And that certainly is the case. Now, Vickrey was the first to discover this, and he did this in work in the late 50s and published in the early 60s, and then finally won the Nobel Prize in 1996. And he was always at least 10 years ahead of everybody else. And quite a remarkable man. And unfortunately, he received the Nobel Prize, or actually he got the award, but then on Nobel's birthday on December 10th, they always have this ceremony in which the Nobel laureate gives a speech and accepts the award. And unfortunately, Vickrey passed away before December 10th rolled around in 1996, which was very sad. But Paul Milgram stepped in and gave Vickrey's talk. And it's actually interesting because the talk that Paul Milgram gave in 96 was describing how you could use an auction in the communications arena to provide communication services in rural areas that are not economic. And this is very interesting because it's something that Paul and I have been arguing for many decades. Because in the United States, the way we've had this universal service fund, which is about $10 billion a year, or was, and in order to provide telephone service in rural areas. And the money had always been allocated based on this cost model, and the cost model was always wrong. And so the system was gamed, and it really was mostly a big waste, especially when mobile communication came around, and they didn't even initially consider mobile as a communication technology. They fixed that, and now they fixed the whole thing. And so now we do what Paul talked about in 1996, which is we have an auction. And so let's see, beginning on October 29th of this year, we'll have an auction in the United States where the FCC is allocating $16 billion of subsidies to service providers that are willing to step in and provide broadband communication services in rural areas that are not economic. And you can guess the form of the auction. It's going to be a simultaneous clock auction, has some package elements. So we'll talk about it later very briefly when we get to applications. but essentially, it's a good example of powerful auction design using very simple, straightforward methods that's going to lead to a much improved allocation of the 16 billion than the FCC would do otherwise. So I think that'll be fun, and it's definitely a multi-unit auction. So there's many thousands of rural areas in the United States. So we'll talk about that a little bit later. Okay, so just to build intuition a little bit, let's jump back quickly to the complete information case. So now bidder A's got a value of 15 euros and bidder B 10 euros, and there's just the two of them. So English auction, what happens? Well, the price gets bid up until we hit 10 euros, and then bidder B drops out, A's the winner at a price of 10 euros. Second price auction, what happens? They both bid their values. The bidder A wins and pays the second highest price, 10 euros. First price auction, here the bidders will optimally think about the trade-off, and A realizes that they can get away with bidding 10 plus epsilon and still win, and so does that. So A wins and pays $10 plus a penny, 10 euros, sorry. And of course, the Dutch auction is the same, so that we get the exact same outcome, 10 euros. And bidder A wins. So we get the same outcome for all. So, so it works for full information. That certainly isn't a proof that it works for incomplete information, but I gave a lot of intuition for the incomplete information case as well. So, so this is, so it's it's quite clear that when I have a single item and I've got any of these standard forms, then the revenue equivalence does apply. However, things like risk aversion, asymmetries, interdependent values, all those things apply in practice. So it's still the case that auction design matters, because in the real world, there's all these other factors that take us away from the revenue equivalence theorem. And so it really does matter, both in terms of efficiency and in terms of revenues, which auction format we choose. And of course, there's lots of issues surrounding, we've assumed so far that there's other assumptions too, like no collusion, the bidders are bidding competitively. And that's sometimes true, often true, but sometimes it's not. And so in designing an auction, we actually have to tailor the rules to try to minimize the scope for collusion. And then there's other issues too, like budget constraints. And so all of these practical realities impact the auction design. So auction design, it definitely doesn't end when Vickery discovered the revenue equivalence theorem that, oh, it doesn't matter, anything works. Auctions are great. We get efficiency and high revenues no matter what we do. And that's just not right. There's still a lot to do because of all the realities. Okay, so one thing is there might be a lack of competition, and so one thing that we might want to do is have a reserve price. In fact, almost all auctions have reserve prices, so they're very natural. Some auctions, the auctioneer actually commits to having a zero reserve price, And that's done not because they don't understand what a reserve price can do, but because they understand that having a zero reserve price very much encourages participation. And participation is extremely important. And so the places that enforce a zero reserve on their auction platforms, such as Ritchie Brothers, which sells large construction equipment, they just have this rule that there's the reserve price is zero. Everything sells, and it actually works really well. It definitely brings the market participants, the bidders that are thinking, oh, well, I may get a really super deal on this backhoe because it might be that nobody else shows up for backhoes. And so it's going to go all the way down to zero. But what happens is people do show up, and that doesn't happen. And so it sells at a much more reasonable price. Now, but what the theory tells us is that if we had a fixed set of bidders, then, so we've got these n bidders, then what we want to do, if we're focused on revenues and not efficiency, is set a reserve price. And you actually want to set a fairly significant reserve price. And we will, we'll find out what the optimal reserve price is, but it turns out that if you use the optimal reserve price, we still get the same result. That you want to set the same reserve in all cases, and that the revenues are identical in all the standard auction formats in expectation. And so that's something we'll talk a little bit more about later. Okay, so just to get the blood flowing, it's early in the morning here in Del Mar, it's getting late in your day. So let's do an exercise. And so what you have here is a jar of coins. It's just two pictures of the same jar of coins. And I have to use images because of our virtual reality here. But what I want you to do is look, we're gonna conduct an auction for the jar of coins, and you won't actually get the jar of coins, you'll get the monetary value of the jar of coins. So, and you can see the coins, they look like they're cents. In fact, they are. So the only thing you have to figure out is how many cents are in the jar. Okay, and if if it turns out that there's 550 cents in the jar, then it would be worth 550 euros. So you would want to bid. We'll do all the bidding will be in cents. I would. Let's say I estimate and it's 550, then in a second price auction, I might want to say, well, I estimate it's 550, and so I've got incentives to bid my value, so I'll bid 550. So that might be a reasonable bid. What I want you to do, so this is where we're going to use chat. So now if you could go to chat, and I'm going to send this to everyone, but what I want you to do is send it to just Mark. Okay, so I want you to go into chat, and you want to send a message to Mark privately, because you're going to be sending bid information. You don't want to send everyone in the class your bid information. That would be a very bad strategy. So make sure you change that to Mark. Now I'm going to change mine back to everyone. I'm looking at my chat box as if you could see it, but you can't, of course. But I'm going to send this to everyone. And then when I send the message, you'll be able to see. So what I want to do is, first I'm going to write down my name. So I write Peter. And actually, if I hit enter, then it'll actually send the message. So I don't want to do that. I want to do Peter, comma, and then E equals 550. Okay, E is my estimate. So E for estimate, comma. And then first, so I just write 1ST equals, and now I'm giving my bid in the first price auction. Okay, so now, okay, a thinking cap. Okay, Peter's thinking, okay, I want to shade my bid. How much do I want to shade my bid? Okay, I've got to solve this differential equation. How many bidders do we have in the room? We've got 18 minus 2, because it's just going to be the 16 of you, not Mark or me, that's bidding. Okay, so 16 people. Oh, this is a hard differential equation. Just 1 second. Okay, I'm going to do 518, first price auction. Okay, I solved the differential equation and I computed that I should be bidding 518. Okay, second price auction. If it was second price, okay, now Peter puts on his thinking cap again. Okay, I estimated 550, second price auction. Let's see, I learned I should bid my value. Okay, I estimate 550, so I'll bid, let's say 550. Okay, I've got it, and now I submit it. Okay, so now you should, in the chat box, you should be able to see Peter's bid. Estimate 550 in the first price auction. I'm competing with, this is fictitious because I'm not actually competing with you, but you're gonna, all 16 of you are gonna be competing together. And then you give your bid in the first price auction, you give your bid in the second price auction. Okay, but make sure you sending this privately to Mark. Okay, that's the first thing you do. And then just type in your first name. We'll just do first names. Hopefully it looks like we're okay on first names. Yeah, I don't see any redundancies, not even for names like John and Peter. So that's good. And then, so I'll let you think for a moment. And then what we're going to do is I'll actually auction this off with a clock auction, but not quite yet. I'll first wait until you've had an opportunity to submit your bids to Mark. And you don't have to think too hard. I think it's half your grade. Is that right, Mark? So I'm just kidding. This is just for fun. So you should have a good time, do whatever you like. And let's see,
Okay, I think we have 9 bids so far.
Okay, 9 bids so far. So if you haven't put your bid in yet, please do.
Okay, we're 11, 12. How many do we have? 16.
Yep, so a few more.
Okay. Okay.
Are we getting close to 16?
Yeah, we're at 14 now. So
okay, so I'll give you another 30 seconds.
Yeah.
And otherwise the bidding window will shut. When the bidding window is shut, it's just like at the FCC. It's over. You didn't get your bid in time, and that's it. Sorry.
Okay, 15 now. So I think I almost got it. Almost everybody has placed their bids.
Okay. So another 10 seconds. Okay. So we'll close it there. And so you got 15 bids?
Yes.
Okay, that's pretty good. So one person is having trouble with the chat box, or more likely getting a glass of water or something like that. Okay, so now, so Mark's going to be looking at the estimates and the bids and determine who won in the first price auction, who won in the second price auction, and what they paid, and also what the highest estimate was in those two cases. But what I'd like to do now is run a ascending clock auction where we're going to start at a low price, and you'll all want the jar of coins, and I'll raise the price until everybody drops out. Now, this is a challenge because they don't, so there is, I don't see anything like raise hand. I know in WebEx, you have this thing called raise hand where you can click it, and that's what I was going to use, but I don't see anything like that. Oh, actually, I know what I can do. I can see your microphones. So what we'll do is,
I think, sorry to interrupt. I think they can also push these green or red buttons. For example, at my name, I have now this green confirmation button. So they press the confirmation button if they're still in, and maybe red if they want to drop out.
Oh, yeah. I see a hand. Okay.
Thumbs up, yeah, or something like that.
Oh, thumbs up. Okay. How did you get those?
I think it's in the.
Is that like reactions, or is that something else?
I think if you click on participants, you can do it.
Yeah, well, I see what other people are doing, but I don't see how I do it for myself. But I guess I do it with the reactions. I can do like thumbs up and I see the more mute rename profile. No, huh? Okay, well, hopefully you guys can figure it out. And so what I'd like, so I see Tim has a thumbs up. Can others do just indicate everybody indicate a thumbs up, because the price is 0. Who would like this at 0? Yeah. So let's get all those thumbs up. And more thumbs up. Other people are having I had a hard time. I couldn't figure out how to do it, so we're learning. Okay, can I get a few more thumbs up at 0? This is a really nice jar of coins here.
I think one participant said that the thumbs up disappears automatically after a certain time.
Oh, so it's difficult to draw. Oh, okay.
If you click on participants or Teilnehmer in German, don't you have the opportunity to do like these green or red buttons?
Oh yeah, I've got this button. Oh, yeah. Okay, yes, no. Okay, let's do that. Get rid of the hands. Let's do yes, no.
Yeah, and exactly. And then they could like switch to red as soon as they want to drop out.
Right, yeah. Sure. So there you can see I am green. And then when I want to drop out, I just go X.
Yeah, exactly. Yeah.
Yeah. Okay, good. Okay, so we're all in. We're all in. This is great. 0. Wonderful. Thank you, Mark. I'm just learning these fancy features. Good. Okay. Okay, so everybody should be in. I've got 15 in. Good. That's great. 16 now. Great. Okay, everybody's in at 0. Okay, so what I'm going to do is I'm just going to call out prices just like an auctioneer. And as soon as we get to a point where you're uncomfortable and you want to drop out, just click the no and you will be removed. And we're going to continue upward until everyone is, there's only one yes remaining. Okay, good. So, and so we're at 0. Let me jump to 100. I'll now do smaller jumps, but obviously there's at least 100 in there. and then 120, 140, 160, 180, 200, 220, 240, 260, 280, 300, 320, 340, 360, 380, 400, 420, 440, 460, 480, 490, 490. Okay, so we've got our winner. Tim is our winner. Congratulations, Tim, at 490. Yes, great job. So now, actually, let me tell you how much you've won, and then we'll go to the first price and second price results. So yes, the good news is that you won. And if winning is everything, then that is fantastic. But the reality is there's only 300 cents in the jar. So you actually owe me €2.90. But we did it for fun, so that's okay. So that's good. That's exactly what I wanted to have happen. I wanted to make money in this. This is great. Auctions are really effective. Not only can we not only get high values and high revenues, we get revenues that exceed value. So that's great. And that's called the winner's curse. So it actually has a name because it's so prevalent in auctions, especially when parties are inexperienced. After a lot of experience, then one learns to account for the winner's curse, and so it shouldn't appear. But now I want to turn to Mark and find out first, Mark, what is the highest estimate among the 15 bids submitted?
The highest estimate is 2,000.
2,000. Okay, that's pretty high. What's the lowest estimate?
340.
340. Okay. So this is very interesting. And now let's turn to the first price auction. Who had the highest bid in the first price?
The first price highest bid is 1,500.
1,500. Oh, so Tim, actually, you should feel pretty good. You lost money, but you didn't lose quite as much as in the first price auction. So yeah, that's quite a loss.
That's also from the person with the highest estimate as well. So highest estimate, highest bid.
Oh, okay. Excellent. That's just the way it should be. And now the second price auction. So now Mark has to do a little work because he's got to find the second highest bid.
Do you want to hear the highest bid as well? Or?
Yeah, I want to hear the highest bid.
Okay, yeah, the highest second bid is 1,999, and the second highest bid in the second auction is 1,050.
Okay, so the price then is 1,050.
Yeah.
So in all cases, I actually was able to sell this jar of coins for substantially more than what it's worth. And in fact, the old days when I was teaching MBAs at Yale, I would do this exercise, but since they were MBAs, I wouldn't do it for cents. I would do it for larger stakes, and actually, at least buy a lunch or two from the proceeds, because they wanted to pay for cash. But with PhD students, we don't want to do that. So this is just for fun, but it illustrates perfectly the winner's curse. Because what happens is, this is quite different. Before I was just talking about private value auctions. Everybody's got a value, they know what their value is, and it doesn't depend upon any information anybody else has. And that's what Vickery studied. And I set this up pretty well because, then I give you this situation, which actually isn't what Vickery studied. Vickery didn't do this. Bob Wilson did this. So this is a common value auction. This is what Bob Wilson did and why he got the Nobel Prize. Because this is an important problem where there's something that's being auctioned. None of us know what its exact value is. We all estimate what its value is. And some of us estimate high, some of us estimate low, but maybe on average, the estimates are unbiased. In our case, the estimates were not unbiased at all. Everybody overestimated, but who wins the auction? The person that overestimates the most, which is exactly what happened. And that means that if you just shade your bid a little bit, you're going to actually lose a lot of money in the event that you win. That, if the estimates were unbiased, then you would do fine on average, but conditional on the event that you win the auction, your bid would be way too high. And that is why you need to understand the winner's curse and address for the bad news that winning conveys. And this is a very general phenomenon that appears in almost every auction or any trading situation. So it's hugely important and is a big leap forward from what Vickery was doing. And this was what Bob Wilson did about 6 years after Vickery. And he did it because he was thinking about auctioning oil tracts. And that's a perfect example of a common value auction. The government's auctioning these oil tracts, which gives you a right to drill for oil. And your task is to estimate how much oil's in the ground. What's the value for this? Well, it's going to depend upon the quantity of oil that's there. So you need to estimate the quantity of oil, and then you need to make some estimate about the future price of oil. And you multiply those two together and subtract your costs, and that's what the thing's worth to you. And notice that everybody else is doing the same thing too, and that they're all facing the world price. The quantity of oil is all going to be the same for all of them. And so it's a perfect example of a common value auction. And so Bob was doing this in the 1960s, and in fact, was hired by the Department of Interior to help them figure out how auctions should be conducted. And in fact, the winner's curse was first described not by Bob Wilson, but by practitioners that looked at the data and saw that the oil companies were losing money hand over fist for multiple decades. So they were bidding in these auctions and, constantly losing money, overbidding. There was one bidder, Shell, that actually made money over the decades. Everybody else lost money. And they're trying to figure out, why are we all losing money? And it was because they weren't doing the proper conditioning of their bids. When I mentioned last time that I worked in Exxon's research park. And so I knew about the winner's curse because this was much later. This was in the late 70s. And so I knew about Bob's paper. I knew about the winner's curse. And I was interested in bidding strategy. And I was thinking that I could use some game theory tools to help them in their bidding. And I got to talk to the guys, and ultimately they didn't want my help because they said, well, we actually know what we're doing. We estimate what the value is and we bid 10 cents on the dollar. And that seems to work. And I thought that was pretty interesting. And then I looked at Bob's work, and if you model the form of uncertainty that you tend to have in these oil tracks, the values tend to be log normally distributed because there's a lot of random events, and your value is the product of a bunch of random things, like the price of oil times the volume, which is length times width times height. And so the log normal distribution works out really well. If each of those things was normally distributed, then the product of normally distributed things is log normal. And then Bob computes the equilibrium bid function in that environment, which it turns out takes a very simple form. You bid a percentage of your estimate, which is exactly what Exxon was doing. So that was kind of neat. And it shows how dramatic it is. They estimate the thing's worth 10 billion, they bid 1 billion. The shading is enormous because the level of uncertainty is so enormous. But it's a very good example of, it's probably the best example of the winner's curse, but it applies for everything. I mean, you think about financial securities, you're participating in an auction of financial securities, then it still has a very strong common value element. These securities are being bought for resale, so everybody's value is dependent upon what to first order, what the resale value is going to be, which is the same for everyone. Now there's our private value elements, where we each have different portfolio positions. And so this particular asset might contribute more to me than you, and that sort of thing in terms of managing my risk. So there's second order factors that are these private value elements. And of course, we're very interested in theories that accommodate both private and common value elements, which we will certainly very briefly discuss. And then in the auctions and market design class, the sequel to this course, we will go into much greater detail. Let's see. Okay, this is actually a distribution of bids from a prior class. This was actually one of Axel's classes. That's Axel's jar of coins. It's sitting in his office in Cologne, I suspect. And when you look at this, actually, these guys. So it's partly the fact that you were handicapped by just being able to see a photograph rather than the actual physical jar. It's the human mind can do much better in estimating when you have more detailed information. That actual physical sighting of the jar would have helped a lot in bringing your values closer to reality. But in this class, this was the undergraduate game theory class, you can see that their average bids are actually pretty much unbiased. But just like in this class, the highest estimate and the highest bid is way far to the right. And actually, this looks very much like a log normal distribution, which is sort of interesting too. But this is certainly my experience. Now, if we had, let's say, actually for a jar of coins, I would guess that the distribution of estimates would be more normally distributed, not log normally distributed. And in the case of the normal distribution, I think this looks log normal a little bit because it bumps into zero. Which the normal distribution doesn't. But obviously there was a positive amount of coins. Now, with the normal distribution, you're actually, the best strategy is to shade your bid by some number of standard deviations. So what you need to do is you need to estimate your value, estimate the standard deviation of everyone's value. So I don't know what estimate they're making, but I have a rough guess that, maybe what the standard deviation is. And then you can actually, figure out, well, if there's 15 bidders, how biased is the highest estimate? And with 15 bidders, it's biased about 1.5 standard deviations. If I get 15 draws from the same normal distribution, and I say, what's the highest? It's going to be, the highest is going to be biased by about 1.5 standard deviations. I can't remember it exactly, but it's in that ballpark. So what does that mean? That means that in a second price auction, or in the English auction, the ascending auction, if you don't shade by at least 1.5 standard deviations, you're going to lose money in expectation. So you must do substantial shading. And this is the equilibrium behavior. So actually what Vickery said was right. You want to bid your conditional expected value. Conditional expected, he didn't say it like that because everybody knew their value. So conditional expected value is the same thing as value. But here you have to do conditional expected value. What's my value conditional on winning? The only time my bid is relevant is when I win. Otherwise, I just get zero. So, but when I win, I really care about what my bid is. And so I want my bid to be optimal in that contingency. So that's why I condition on winning. And as I said, in the second price in the English auction, you would then optimally shade by simply calculating what the bias of the highest estimate is with 15 draws. In a symmetric, if you thought it was somewhat symmetric, which it probably is. Now, in the case of the first price auction, you would need to shade more. And so really in equilibrium in the first price auction with 15 bidders, that's a lot of competition. Now we have two forces at work. You want to shade your bid because of the winner's curse, and then you want to additionally shade your bid so you make money. So you actually shade your bid about, in equilibrium, about 1.8 standard deviations, something like that. And if you were super risk averse, then this is actually kind of interesting. In the private value world, risk aversion drives your bid towards your true value. In this common value world, it just does the opposite. If you are really risk averse, what you should do is not participate at all. You should bid zero because, and especially if you think that some of your classmates might fall prey to the winner's curse. So if you're bidding with the more naive, the more inexperienced the bidders, the more you would want to shade or not participate. The reality is there's no bid that can make money in this classroom setting for a jar of coins. I've done this for at least 25 years, 30 years. I've never lost money. I always make money. So, the data is in. And so if you need money and you're teaching or, just even on the street, you can play this game and make a little bit of money perhaps. Good. So let's see, how are we doing on time? 8:06. So, okay, so let's go for another, let's do this. Let's do one more auction or trading situation. We'll sell this car and then we'll take a little break, stretch our legs. Okay, so now I've got this this nice VW here. Golf TDI, perhaps famous, and you want to sell it. Okay, or actually, I want to sell it to you. You're going to be bidding on this used car. You don't know what its true value is. And so the first thing that you need to do is have some information about what it's worth. And you estimate the value is somewhere between 0 and 12,000. And everything's equally likely. Okay, the seller, me, I know the true value. Okay, but it's, it's a nice car, but I need some money and I'm willing to sell it at a price that's, as long as the price is 2/3 of the true value or above. Okay, I know what the car's worth. And as long as I get an offer that's at least 2/3 of the value, I'll be happy. And otherwise I'm going to reject the bid. And my question for you is, how much should you bid? Okay, so just think about that for a moment. Okay, and maybe your calculus is going like this. Well, it's worth between 0 and 12,000. So on average, it's worth 6,000. And that's nice. The seller needs at least 2/3 of the value. So there's only one of you. So it's just you and me here. It's not the rest of the class, you and me. So, given that you need that I need 2/3 of 6,000 is 4,000. So maybe 4,000 is a good bid. What do you think? Well, let's imagine that you do put in a bid of 4,000. Then what's going to happen? Well, then I'll look at your 4,000 bid and look at the value, the true value, and basically I will accept it as long as the 4,000 is more than 2/3 of the actual value. So in particular, I'll sell it to you whenever the value of the car is between 0 and 6,000. If the value was above 6,000, I'm going to keep the car because you haven't made an offer that's within 2/3 of the true value. So let's calculate how much money you've made. So you've won the car, you got the car in all those circumstances where its value was between 0 and 6,000. So that means that the expected value, all those are equally likely. The expected value of the car then is 3,000. And you paid me 4,000 for it. So you just lost money again. You're not doing well today. Sorry, but so that's too bad. That it just wasn't you bid too high. Okay, well maybe just shade your bid a little bit more. Offer 2,000. Okay, offer 2,000. What happens? Well, then I'm going to sell it to you as long as the value of the car is between 0 and 3,000. If it's over 3,000, your offer is insufficient. It's less than 2/3 of the true value. And so your 2,000 bid, your expected value of the car now is halfway between 0 and 3,000 or 1,500. And you paid 2,000, you just lost money again. And in fact, we can go down and down and down. It doesn't matter what you offer, €1 for the car. Then it's you will win whenever the value is between 0 and €1. And so the expected value of the car is going to be halfway between. So you'll win. As long as the the value is over 1.5. And so the car's worth 75 cents. And you just paid me €1 for something that's worth 75 cents. So no matter what price you make, you always lose money. And this is the exact same phenomenon as the winner's curse. And this was done by, also resulted in the Nobel Prize for George Akerlof. And George Akerlof, so this was a very nice paper that ultimately came out in the QJE. It is The Market for Lemons, very famous paper, and argues quite well that in fact, this phenomenon can lead to the complete destruction of markets. So in fact, there's no opportunity. You know, I've got this car, I can't sell my car because I've got private information about its value. And that creates a problem of adverse selection. And that adverse selection is going to prevent, which is the same phenomenon as the winner's curse. In auctions, we call it the winner's curse. In insurance, they call it adverse selection. And in the case of buying a car, I think we borrow from insurance and call it adverse selection as well. But it's general phenomenon, happens in all trading environments. And in this case, the market's destroyed. Now we can fix the market by simply having some way to disclose what the value of the car is. So I can take my car to the gas station and have the mechanic look it over carefully and certify that the brakes work and the engine's in fine shape and the tires are a little worn, and so, you know, as a result, this car is worth 8,000. And then I have no problem. Then a buyer like yourself has no problem in participating in the market. So there are solutions, and in fact, the market institution has evolved to that point. So it's no longer the case that I can, hide the fact that the brakes don't work. I can't hide the fact that the engine's broken. All these things I actually have to disclose. And the same thing, we just sold our house in Washington, DC when we moved to California. And same thing, I have to disclose all the things that don't work, that a buyer would expect to work. The washing machine, the air conditioner, the hot water heater, the heating system, the absolutely everything. I have to disclose everything that doesn't work. And otherwise the buyer can come back and say, well, I assumed that the air conditioner worked and it doesn't. And, that's on you. So basically the market institution has evolved in a way that is actually very, it's very nice and facilitates transactions. Now there's certain things, like this is a blue car, and I might really love blue, and so I get extra value because it's a blue car, but that's a value that's intrinsic to me and not something that the mechanic can assess some value on. In any event, I'm selling it, so it's irrelevant how much I value blue, although that might impact whether or not I accept your offer. If I happen to be somebody that hates blue, then you've got a even better opportunity. So to strike a profitable deal. So this is very important as well, and quite general phenomenon. Now, one interesting thing. So George Akerlof's paper, it's definitely the paper that gave him the Nobel Prize. That paper he submitted 13 times. It got rejected by everyone. Journal, economics journal after economics journal, rejected every time. So I mention it, so you shouldn't feel too bad if you submit a paper and it gets rejected. You might think, well, actually, I know it's worthy of a Nobel Prize, and I should just send it to somewhere else. That's generally a good strategy. And this is not unique to Akerlof. So if we look at Meyerson's optimal auction paper, which was certainly one of the most important papers that gave him the Nobel Prize, that paper came out in Math of Operations Research, which it's not even an economics journal, and it's not even a premier operations research journal. So it's, strange things happen. But this winner's curse and adverse selection, extremely important, and extremely important in market design. You want to structure the market to mitigate the winner's curse and to mitigate adverse selection. The way we do that in auctions is, one, we have a data room where we present all sorts of information about the item or items being sold. So people really understand, have a good way to estimate more precise values. And then we run an auction that facilitates price discovery, and that mitigates the winner's curse and enables parties to bid more aggressively. Now, what we found, and what you actually find in theory, is when you're dealing with sophisticated parties that are playing equilibrium bidding strategies, what we find is what I just said about price discovery enabling bidders to bid more aggressively, and that actually is Paul Milgram's result, and that got him the Nobel Prize. He did lots of other work, but that was one of the, that's certainly his key insight in the Milgram-Weber and his other papers written in the early 80s and late 70s. And that turns out to be true with experienced participants bidding equilibrium strategies. But as you can see from our classroom exercise, it's not true when people are bidding with less experience and more casually. So what happens in the classroom is the first price auction yields the highest revenue. The second price yields similar but lower revenues. And the English auction, or ascending clock, yields the least revenue. And the reason is the English auction, people are learning about the winner's curse from the dropouts of the others. So the conditioning that's required for equilibrium behavior is much more transparent in the dynamic process than it is in the sealed bid process. And so people are apt to realize that their estimate is a gross overestimate if they're bidding a lot and they see everybody else drop out. Your inference from the dropouts of the others is like, well, these guys, that lots of people are dropping out at 350. Why are we getting all these dropouts at 350? They must have estimated it at something much lower than I did. I estimated it at 2,000, and we got guys dropping out at 350. Maybe my 2,000 is too high, and so maybe I should revise my estimate to 1,000. And that's exactly what happens, and I'm sure happened this afternoon for you. And so we end up getting a much lower price with this dynamic process in this case. But really, that's an artifact of you're not playing equilibrium strategies and you're being fully vulnerable to the winner's curse. But in situations where the participants have an opportunity to learn, so a repeated auction setting, then they in fact do learn, and the English auction actually performs better. So there are some very vivid examples of the winner's curse, even when the stakes are extremely high. So sometimes people think that, well, yeah, when you do a classroom exercise or a laboratory exercise and the stakes are 20 euros, then of course people don't behave optimally. They're going to screw up. But when they're bidding 10 billion euros, then they don't make mistakes. They hire experts, they study the problem real carefully, and they'd never do something like this. Well, that turns out to be false. The spectrum auction is a very good example of a very high stake auction where some of the bidders make very large errors. And a good example of that is the 3G auction in Germany. It's probably the best example, where the prices got bid up super high. This was in 2001 when you were all very young, but perhaps you remember it. And in 2001, it was right at the end of the dot-com boom, and which was also a telecommunications boom. And so people had sort of inflated ideas of what the future would look like. But in any event, in that auction, very competitive auction, Germany was thought to be a key market within the larger European market. And so the competition was pretty intense. The price for a license got bid up to 8.5 billion euros. And the last bidder to win of the 5 winners was Mobilecom. And after, so they won, they paid their 8.5 billion. And then a year and a half went by, and then they just gave the license back to the government and were not reimbursed anything. So they realized that this thing wasn't worth substantially more than 8.5 billion. It was actually worth to them less than zero. And the reason is, being the number 5 player in Germany is just not that great. It's super expensive to build out Germany because you've got the population dispersed over fairly difficult terrain. And so it just cannot support that many bidders, that many winners building infrastructure. So very clear example of the winner's curse that effectively all the market participants fell prey to, even though they should have been more sophisticated, in my mind. I mean, to me, I thought the prices were grossly inflated, and a lot of prices were grossly inflated during the dot-com bubble. Okay, so that's the winner's curse. We can address it by conditioning on the bad news that winning conveys, as I said, and this is a factor that you need to consider in every market design. There's this, that when you combine uncertainty and competition, you get this potentially dangerous mix, and from a bidder's perspective. And so you better know what you're doing. And what you should be doing is, recognizing that conditional on winning, your estimate of value is biased, and you need to make that adjustment. Okay, and now we're going to talk about multiple item auctions. So, as I said last time, one of the interesting things is the literature focused almost exclusively on single item auctions, right up through the beginning of the 80s, and with a few exceptions like Vickery and Wilson. But auctions in practice almost always involve auctioning many items. And so that's why we're talking about it. It's very important. sorry, normally I advance with the space bar, but I've got to be in the right spot. So, yeah, so what we're going to actually, first what I want to do is introduce equilibrium in games with incomplete information. And then we're going to talk about mechanism design. So the theory of how to extend games with incomplete information. And then I'll talk about auctioning many similar items. So divisible goods and multiple products and that sort of thing. Then I'm going to talk about revenue equivalence in a much more general way. And I think that'll be quite useful. It illustrates the full power of mechanism design. And then finally, we're going to talk about applications. Now, we're not going to do all this today. In fact, we're going to do, we'll just get started with equilibrium of games with incomplete information today. And maybe begin mechanism design, but I doubt it. I'm pretty confident we'll just do the first bullet. So now we're going to jump into some math, and hopefully everybody's comfortable with calculus and the like. That's what we're going to need when we do games with incomplete information, because we're having to take a lot of expectations and sort of integrate over the value distributions of others and that sort of thing. So that's going to involve differential calculus. And so let's just jump right into it. So first, so now we're still back on a single item, but what I want to do is formally do the trade-off between probability of winning and terms of trade that one faces in a first price auction. So this auction, and it's the simplest setting, it's going to be independent private value, and the bidders are going to be risk neutral and symmetric. So we're going to have n bidders, and we're going to draw each bidder's value independently from the same probability distribution F. And so the first thing to do is to write down what your objective is, which is going to be your expected profits. So we have symmetry, so I'm just going to pick one bidder and write down what the bidder's profits is. And it's going to depend upon what their value is, of course, and on what their bid is. And so what is it going to be? Well, what you're going to get conditional on winning is value V minus your bid B of V. So that's the profit that you get conditional on winning. You get 0 when you don't win, so we just ignore that. That's 0. And I've got to multiply that by the probability that you win, conditional on your bid. Your bid is going to definitely influence whether or not you win. So that's our expected profit, and that's what I would like to optimize. Now, and the standard way to calculate an equilibrium would then be to take, I've written down my objective, I take the first order condition and set it equal to 0. That gives me a differential equation. I have a boundary condition. Maybe my boundary condition is when my value is 0, I bid 0. And then I solve the differential equation. And I've got one for each bidder. And so I solve the system of the n differential equations. I exploit symmetry. So all our differential equations are the same. And so then I'm solving a single differential equation in order to find out the optimal bidding strategy. So that's what we would do in general. But in this case, I'm going to be a little bit more clever and do it without any differential equations. And I'm going to do this by exploiting the envelope theorem. And but let's just look at what the derivative of profit is with respect to value. And here I've got to recognize that profit depends on both value, but also, directly on value, but it also depends indirectly on value through the bid function, because my bid depends upon value. That's what I'm trying to find out, what my bid function is, but we're going to assume safely that the bid function is an increasing function of value, which will turn out to be the case. So the total derivative here of profit with respect to value is the partial of profit with respect to my bid times the partial of bid with respect to my value, plus the partial derivative of my profit with respect to my value. Now, what the envelope theorem is telling us is that, well, bidders are setting their bid to be optimal, so the derivative of profit with respect to bid is going to be 0 at the optimum. So this is 0, which means that the total derivative is just the partial derivative with respect to value. So it's the partial derivative of profit with respect to value. But let's look at this. What's the partial derivative with respect to value? That's just the probability of winning, right? Because this is the only place that V enters directly. And so it's the probability of winning conditional on my bid. But here we're going to recognize that it's a first price auction. So who wins? The guy that bids the highest. Okay, so it's the probability I've got the highest bid. But now we're going to impose symmetry, and we're all have the same problem. We're all going to, so the bid function is going to be the same, and it's going to be increasing, which means that having the highest bid means that you have the highest value. But what's the probability I've got the highest value? Well, we've got n draws from the same distribution f. The probability my value is higher than yours is f of v. The probability it's higher than each of the n minus 1 other bidders is f of v to the n minus 1 by independence. And so now I know a few things. I know that this total derivative is equal to f of v to the n minus 1. And now I can determine what the expected profit is simply by integration. Okay, I just integrate this, and that's the fundamental theorem of calculus. Okay, that I can integrate the derivative, and that's going to be the profit up to a constant, and here's our constant of integration, which is just the profit that I get when my value is 0. And but this, what is my profit when my value is 0? Well, I'm actually going to win with a 0 probability then, and there's no scope for me to make money, and so that's going to be 0. So that's just equal to this integral. And now I can substitute into, now I know what this is, and I know what this is, this probability of winning. And so, and I know what this is. I just calculated it. And so then I can solve for B of V. Okay, so now I just by flipping this over to this side and shifting, so just by flipping and shuffling, I get the following, just solving for B of V. So there you go. I found the equilibrium bid function in the symmetric independent private value case without solving any differential equations. So that's kind of neat. And this all makes sense. So this is, so I bid my value minus, and then I'm going to do some shading. And how much do I shade? Well, it depends upon the distribution of values. And basically I'm going to be integrating from 0 to V, from 0 up to my actual value. And what am I integrating? It's going to be f of u to the n minus 1, where u is the integrating variable, and divided by f of v. So it's actually f of u over f of v to the n minus 1. Since f is a probability distribution, it's a increasing function between 0 and 1. So I'm basically integrating something that's between 0 and 1 and from 0 to v. And so it's going to, that's what I need to subtract. And if we look at an example, let's just take the uniform distribution, which is the case that's used almost 100% of the time in the laboratory. Then I simply want to bid n minus 1 over n times my value, just plugging in the uniform distribution where f is equal to v. And what can you see? Well, you can see, as we add bidders, I'm going to bid more and more aggressively. I shade my bid less. And so if there's 2 bidders, then I bid half my value. If there's 3 bidders, I bid 2/3 of my value. If 4 bidders, 3/4 of my value. And in the limit, I bid my full value. So this all makes a lot of sense. Competition raises the revenues, and the revenues reflect true value as we converge to perfect competition. So that's all very nice. Good. Okay, so that was the first. So now we've done a full analysis of a game with incomplete information. What I want to do now, and we'll just start this. I'll just set this up. I don't think I'll be able to get through it today. Oh yeah. I should be able to get through it because we go until 9:30 my time. So we've got 40 minutes. Good. So yes, what I'll do for the remainder of today is look at another game with incomplete information, which is a simple game, and I'm going to just directly calculate the equilibrium strategies for this particular game. And it's an important game because it's bargaining with incomplete information. It was first studied by Chatterjee and Samuelson, and it was published in Operations Research. It's a very fine paper, and I know probably should have been published in a top economics journal, but anyway, Operations Research is a top tier OR journal, so good place. But this is a problem where the seller and buyer are engaged in trade, and they're bargaining with one another. The bargaining is complicated because each has a value, and they don't know what their values. They know what their own value is, but not what the value of the other is. And as a result, there's some incentives to act strategically. And of course, how you act depends upon what game you're playing. So there's lots of bargaining games we could play. We could have them alternating offers over time, and we could have them, one party makes a take it or leave it offer, and that's it. They trade or not based upon whether the other accepts the take it or leave it offer. So there's lots of things we could do. But what Chatterjee and Samuelson do is a very simple bargaining game, which is split the difference trading, where both sides make an offer, and if the offers are compatible, then they trade, and otherwise they don't. So if the seller's offer is below the buyer's bid, then they're going to trade, and they'll split the difference halfway between the two, and otherwise they don't trade. So a very simple trading rule. It's actually a trading rule that I first did actually right before reading this paper. I actually, this played out in when I was a PhD student. I was sitting at Stanford and in my office, and my office mate, Denny Yao, who's at Harvard Business School, he noticed that he was 2 years ahead of me, and so I was taking the same micro theory class that all the PhD students take. But since I was 2 years after, I had the latest edition of the textbook, and he had the older edition. And he thought that he valued the most recent edition more than I did. And so he wanted to get the latest edition. And I said, sure, fine, let's do this. Or consider this, but we of course have to establish that I value the latest edition more than the old edition, and so why don't we do this? Let's just both write down a number on a piece of paper, and that indicates the amount that we value the current edition more than the old edition, and if you bid more than me, then we'll trade, and we'll trade at halfway between. So we did this. We were office mates. So this was all very friendly, but just recognizing the fact that of course it's going to be worth more to me. It's going to be that I value the latest edition more than the old edition, and same for him. But it's certainly possible that he values the latest more than me. So we both wrote out numbers. As it happens, we both wrote down $13. And so we ended up trading at $13, which was just fine. Now, it's kind of interesting because, what would have happened, according to the rules, if I wrote down $13.50 and he wrote down $13, then we were supposed to not trade. But maybe what I would realize is that, well, I was pretty clever, and I actually exaggerated a little bit, because I knew that by writing down a bigger number, that would improve the terms of trade in the event that we do trade. And he might have done something similar. So if I write down $13.50 and he writes down 13, there's probably gains from trade still. And so maybe I'd suggest, well, okay, we're close enough. Why don't we just trade it? We're office mates. Let's just trade at $13.25. But of course, if we're going to do something like that, then that's going to affect our equilibrium bid strategies. And I'm not going to analyze that game where we actually are playing this dynamic game, and we're going to do something different based upon what offers we make, and we're going to be learning from the sequence of offers. We're just going to keep it very simple. But my point is that this game actually has a lot of commitment built into it, that And it was right in my wheelhouse at the time, because my dissertation that I was working on was bargaining with incomplete information. So this is sort of exactly the sort of problem that I was interested in. And anyway, here's the analysis. So we've got a seller, we've got a buyer. Their values are drawn from probability distributions. And they're drawn independently. The payoff is going to be just what we call quasi-linear utility, which is just for the seller, it's price minus value, so P minus S. For the buyer, it's their value minus the price that they have to pay in the event of trade. And of course, it's zero for both of us if there's no trade. So very straightforward. And the private information, the seller knows S, the buyer knows B, and the probability distributions are in the form of the utility functions. This quasi-linear utility is all common knowledge. So now what we need to do is figure out what the equilibrium bidding strategies are. So, or the offers, since this really isn't an auction. So the seller, I'm going to just, their strategy is going to be how much, there's no learning in this. It's just a one-shot sealed bid. So the seller is going to be offering P of S, and that's their strategy. How much they offer is a function of their private information. And similarly for the buyer. So I'll just use my notation will be Q of B. So Q is not quantity, it's just it's a letter that indicates their bid function. And my task this morning is going to be to figure out what those equilibrium bid functions should be. And this is not what I did in the textbook case. I just wrote down, roughly wrote down, I don't even remember what my value was, whether it was higher than $13, but not dramatically so. I just, probably too honest. Which isn't such a bad thing in a repeated game when you're dealing with your office mate. Okay, so so this is the game, which I've already described. And now the first thing you want to do in any game of incomplete information is write down what the payoffs are for the players. So we're always going to, in economics, we start out, what's the objective? And we're going to try to make decisions to maximize that objective. So the first thing I have to do is write down what the objective is, right? And with incomplete information, it's always easiest to start with the ex post realizations. And then the interim decision state, before you learn the private information of the other guys, you'll then be just taking expectations over the other guy's private information. So we start with the ex post. My ex post payoff is going to be just price minus value for the seller in the event we trade. When are we going to trade? Whenever my offer is less than or equal to your offer. The offers are compatible. The seller is below the buyer. And it's going to be zero otherwise. And similarly for the buyer, it's just B minus P, the buyer's value minus the price they pay. In the event that we trade, the offers are compatible, the seller is below the buyer. And what is price? Price is just, in the event we trade, is just split the difference, halfway between. So fair. Fairness is a good thing. So this is a good fair rule. So let's, instead of working this out for general distribution, let's specialize to our favorite distribution for simplicity, which is the uniform distribution. And hopefully that will make things a bit easier. So then what I want to do is then my objective is just going to be for the seller is just going to be my ex post payoff, the price minus S, taking the expectation over all the possible buyers I might be dealing with. So I take the expectation over B. And same thing for the buyer. Okay, so we're both going to be doing the same thing, and we're going to be choosing our offer functions, P of S and Q of B, to maximize that expected payoff. So that's all we're doing. Very straightforward. And so let's do it for the seller, and then the buyer is going to be symmetric. So I'll just write down what it is for the buyer. But let's start with the seller's problem. So, and let's assume that these offer functions P and Q are strictly increasing. That's a very good assumption. So we'll, of course, when we do the calculation and we find out, oh, actually it turns out they're not increasing, then we would have realized that we made a mistake and we'd have to go back and fix our work. But we've got very strong intuition that this should be strictly increasing. And in fact, what we compute is going to be strictly increasing. So our intuition will be confirmed by the mathematical analysis and all will be good. So yeah, since they're strictly increasing, these P and Q functions, the offer functions, will have inverses, and that's very useful. You'll see right now. And so let's have X be P inverse and Y be Q inverse. Because the inverse, the reason the inverse is useful is that tells me the type of bidder that would make a particular offer. So I'm identifying the particular value that would lead to a particular offer. And that's useful because now what I want to do is, in calculating the expectation, so now this is I can simplify my objective. I want to take what we had before, this objective function here. So I am now taking the expectation over all the buyer types, but there's a whole bunch of buyer types where we aren't going to trade. And in particular, when the buyer's value is too low, certainly if the buyer's value is 0, we're not trading. I'm going to have a higher value than you have. So no way we're going to trade. So, and in fact, this whole range from 0 up to this point, Y of B, there's no trade. So the payoff is 0. So it doesn't appear in my objective. Because Y of P is exactly the value. So I'm plugging, so P is P of S. I'm sorry, so Y of P, so Y is Q inverse. So this identifies the value of B where the offer is P, and we would then trade because P would equal, my offer would equal yours. It would be actually that exact $13 case where our offers are exactly equal, and it's just the point where we barely trade. So here we're just, and then all other B types, all higher values, since Q is increasing, we're definitely going to trade. Your value is, your offer is going to be above my offer. And what price do we trade at? We split the difference. We trade at P plus Q over 2. And then of course I have to subtract out my value S. So I'm integrating over all these types. The distribution is uniform. So rather than dF of B, I've got dB because the density is 1 for all values between 0 and 1. So that's why the distribution vanished, because I'm dealing with a uniform distribution. Okay, great. So now I've done the hard work. so the hard work is always making sure you get your objective right. But now I've got the objective right. Now I want to do the usual thing. I take the derivative and set it equal to 0. And that gives me a differential equation. And then I'm going to do the same thing for the buyer. And then I'll have two differential equations. And then I'll solve simultaneously those two differential equations. Great. Let's hope we can do it. So, one thing with games with incomplete information, when you're explicitly solving them rather than using mechanism design, you're invariably going to be taking the derivative of integrals, because the interim payoff is going to be this integral. So you have to remember the formula for the derivative of an integral. And if you don't remember it, you should go back and look it up. It is, what you have to remember is there's potentially three things that change. So my variable that I'm taking the derivative with respect to is p. And so it's potentially, the p could appear here in the upper limit, p could be here in the lower limit, and p could appear in the integrand. And so there's actually three terms in general to the derivative of an integral. And the first term is the derivative of the upper limit times the integrand evaluated at the upper limit. But this is going to be 0 because the derivative of 1 with respect to p is 0. It doesn't depend on p. However, the second term is the derivative is minus the derivative of the lower limit, which is minus y prime of p, times the integrand evaluated at y of p. Okay, so when I plug in, so this is q of y of p, but y is q inverse, so it's q times q of q inverse, which is p. So I've got p plus p over 2, which is 2p over 2, which is p. So that's why this is p minus s. Okay, so that's the second term, which is our first term here, since the first term was 0. And then finally, I've got the third term, which is taking the derivative of the integrand, which is the integral of the derivative of the integrand. So I take the derivative of the integrand here with respect to p, which is 1/2, right? Because I've got this divided by 2 here. So it's going to be 1/2. So I'm basically integrating 1/2 from y of p to 1, which is 1 minus y of p. And there's the 1/2 divided by 2. Okay, so those were the three terms, which fall out to be two terms in this particular case, and I set that equal to 0. That's my differential equation for the seller. And then I do the exact same thing for the buyer. And I'm not going to go through it step by step. You can do that yourself, and you get something very similar. Okay, so now I've got my two differential equations. Now I want to solve the system of differential equations. So that's the next step. And at this point, I'm sure you all remember, this is the point where now you can substitute in, once you've taken the derivative, then you can substitute in equilibrium conditions and exploit symmetry and the like. You can't do it before you've taken the derivative. That is, you can't do it directly at the objective state, but you can do it now that we've taken the derivatives and set them equal to 0. So the equilibrium condition is going to be that the S equals X of P and B equals Y of Q, that's follows definitionally from, in equilibrium, this P of S and Q of B are absolutely what I'm doing, and X is P inverse and Y is Q inverse. So this means I can go back to this differential equation, and I can put things, rather than now I've got X's, Q's, P's, B's, I've got too many things. I make this equilibrium substitution so that the differential equation is simply stated in the y's and the x, y's, p's, and q's. And so I've eliminated the s and b from these equations. And so I want to solve this system of differential equations. And there's lots of different ways to solve systems of differential equations. What I like to do nowadays is, first thing I would, there's going to be boundary conditions that are going to be important. And so one thing is I could guess what the boundary condition was. For example, when we're doing the first price single item auction, the boundary condition was obviously you're going to bid zero when your value is zero. Okay, that was a very natural boundary condition. And with a reserve price, you would bid the reserve price when your value was the reserve price. Okay, because there's no benefit in shading. And that's sort of how why the reserve price works in expanding revenues, because it forces people to bid more aggressively than they would otherwise, because it forces basically the guy whose value is the reserve price to bid his full value. And that forces everyone else to bid more aggressively. And hence the increase in revenues. In this case, it's not as obvious what the initial condition should be. It's what should it be? I don't know. So anyway, my favorite method of solution would be, in general, would be I would guess the initial boundary conditions that are typically necessary in order to solve the system of differential equations. And usually, in this case, I've got two differential equations. I'm going to need two boundary conditions, and that's going to then uniquely define the equilibrium strategies. And so I would make this guess, and then I would have Mathematica solve the differential equations, because I'm not very good at it. But in this case, because it's the uniform distribution and the guys are risk neutral, I could guess that the solution is going to be linear. That's the beauty of the uniform distribution. It's got this linearity, and the quasi-linear utility is linear. So maybe there's a linear offer function. And that's what I will assume to solve this system of differential equations. But before I do that, the thing that I can do, Mathematica could do it true for me, but I can do this myself, is take this from a system of two differential equations to a single differential equations by substitution. So I simply substitute the second equation into the first, or the other way around, and that's going to give me a single equation, which is standard practice, right? Whenever we've got a system, when we've got multiple variables, then you solve for multiple variables by, if you've got multiple constraints, by substituting one of the constraints into the other. So that's what I'm doing here. I'm just solving 2' for y of q, and then substituting into the equation one, the first equation, in order to get there you can see the zero if I move my head, it's just zero you're missing. So this is the differential equation. So now I've got a single differential equation. It's a second order differential equation that I need to solve. Okay, so, you can look at that and as I said, let's guess that the solution's linear. That would be a good starting point. So when we guess that the solution is linear, then it's trivial to see if there is a linear solution to this. And in general, it's linear means there's going to be that x of p is alpha p plus beta, where alpha and beta are constants, and we can just plug that in and solve for alpha and beta. And it turns out there is a linear solution. Hooray! We're done, or at least we would be done if the offer functions were increasing. And lo and behold, they are. So that's great. The alpha is positive. Wonderful. And so then I can do the same thing. Now I can go back and substitute into, figure out what the offer function is for the buyer as well. So I actually calculated the inverted, and so I have to invert them, but inverting a linear equation is something that all of you can do in your sleep, I'm sure. So now I've got the results, and this is really nice, I think, unless I made a mistake. And I should have said that the first thing I do when I have a problem like this is I start with my intuition. First am I thinking, well, what do I want to do? What's my strategy? Well, gosh, it sure seems like I need to shade my bid, and or actually, depending on whether I'm seller or buyer, and the question is sort of how much, but I want to bid. If I'm the seller, I'm going to want to overstate. If I'm the buyer, I'm going to want to understate. And sort of the question is how much? And it's important to have this intuition and think about the intuition and recognize that, well, intuitively it should be, the offer function should be increasing. So it's important to have that intuition, because actually these things, once I do the math, then I need to check and confirm that in fact my intuition is confirmed. Because I could have made a lot of mistakes along the way. I probably did. Fortunately on this slide I didn't, because I've done this before and I thought about it. So these are actually correct. But if I was just doing this on my own, I probably would have made a mistake. And then having the intuition is very useful, because it tells me, oh, okay, I made a mistake somewhere. I got some decreasing offer function and that can't be right. So something's amiss here. Let me think back at this. And I go back and I find out, oh, step one, when I wrote down the objective, I wrote down that should be a minus sign and I have a plus sign. So, okay, now let me redo everything. So, anytime you're doing any kind of analysis, it's very important to start with intuition, develop your intuition as much as you can before you do the mathematics, and then do the math and make sure you've got confirmation of your intuition. If you don't have confirmation of intuition, there's two things that happen. One is that you've made a mistake, as I've described. That's usually my case. But the other is your intuition is wrong and you just have bad intuition about this problem. And so, but the math, you go back and you look and it's like, no, it looks right. And then you realize, oh, my intuition is wrong. Here's why. And the math helps you develop your intuition. And that's basically what it's all about. So there's a little bit of a digression, but it is it is important and a good way to think about modeling, that the modeling is, and the more complex the modeling, the less you should trust the results until you've developed your intuition. So my view is you're not done until the answer is intuitive, and then you might be done. But so let's look at this and see if the answer is intuitive. Okay, so what do we got? I've just plotted the offer curves. So here's all the seller and buyer types between 0 and 1. And here's the offers for the seller and for the buyer. And what's happening? The seller is overstating. And they keep overstating. They're overstating less and less and less. And what happens here? They're not overstating at all. Well, what's happened there? At this point, I've reached the highest offer that the buyer ever makes, because the buyer is understating. They're shading. Buyers understate, sellers overstate. This is true value, vertical 45-degree line. So what's happening at this point is, for all prices, all offers above this point here, there's going to be no trade. And it actually doesn't matter what I do up here. But I do want to bid my full value here because there's no benefit from shading. I'm sorry, from overstating. Okay, if I overstate at this point, I get 0. And that's why I'm willing to offer full value. And as soon as we start moving down here, I start making money. And I've just optimized my overstating by the optimal amount. So this actually is, so the two boundary conditions are this point and this point. The lowest seller offer and the highest buyer offer. Those are the two boundary conditions. And that's what's, and it turns out that those boundary conditions are unique if you assume a linear solution. Okay, so I did get uniqueness, but I got it because I assumed a linear solution. It turns out that if I take those differential equations and I say, okay, I'm going to start the buyer here, and I'm going to start the seller here. Those are two different boundary conditions than before, and I'm going to get some nonlinear solution to the differential equations, and it's going to be in equilibrium. So the equilibrium is not unique. It's only unique once I assume linear strategies. And it's not that it is, the linear strategies are unique in the space of all strategies. I'm sorry, they're equilibrium strategies in the space of all strategies. But that is its role, though those are best responses, mutual best responses, allowing parties to do anything, outside of linear strategies. But there's lots of other equilibria, and in particular, if I overstate more, so if I have a boundary condition up here, then what's going to happen is you're going to actually have an incentive to overstate less. So it's going to force you to bid more, to overstate less. And in the extreme, I can make a take it or leave it offer at some point, and that could, and then your response is going to be to exaggerate, to understate 0. You'd bid true value at that point. you actually wouldn't bid true value. You'd bid whatever, the fixed thing that I'm offering. So we both offer the same thing. So this is, now some folks would say, some theorists would say, well, okay, the equilibrium is not unique, so this is a poor theory, and I'm not really interested in it, and I'm only interested in theories that have unique equilibrium, a unique equilibrium. So I completely disagree with that, and especially in the bargaining domain. Because bargaining, if we experimentally test this, and this has been done by lots of people, what you see in terms of outcomes is snow. It looks like a TV set from 40 years ago on UHF. It basically is just snow. There's trade all over the place, and so what I'm saying is, if you do this experimentally, you'll reject every theory. Doesn't matter which unique outcome your wonderful theory produces, it's going to be strongly rejected by the data. So does that mean that we shouldn't do theory in bargaining problems? No, it just means we shouldn't expect that, we shouldn't be upset if somebody suggests a bargaining model that doesn't have a unique equilibrium. Because the way you get a unique equilibrium in bargaining is by imposing a whole bunch of restrictions to make the, which may or may not be somewhat plausible, but there's no way that if you get uniqueness, that I would say, okay, well, that's the equilibrium that we should expect in the laboratory in a bargaining context. The reality, as I said last time, is that bargaining is inherently indeterminate, and no economic theory is going to 100% explain what's going on. In fact, we'd be lucky if we could explain 20%. That was my conclusion yesterday, and it remains my conclusion today. So one interesting thing when we look at this is a lot of gains from trades were lost. Basically, the gains from trade had to be at least a quarter, or we would have no trade. So the outcome is obviously inefficient. And the reaction to that might be that this is a bad mechanism. So maybe that's the case, that this is just Chatterjee and Samuelson weren't smart enough to think of a good mechanism. And so they got this inefficient mechanism, and that would be a reason to reject the paper, because it's so inefficient. So what we're going to do next class is prove that, in fact, no, Chatterjee and Samuelson got this just right. They picked the optimal mechanism for this trading environment, that this, in fact, is better than anything else that you could propose in this context. So that'll be kind of neat. But in order to prove that, we're going to have to switch to mechanism design and use the full power of mechanism design that was enabled by Meyerson's work in the late 70s. And so that's what we'll turn to in our class Monday. We're going to have a weekend where we don't have class, and then we'll come back on Monday and do the analysis. So with proving the result that essentially was one of the two big results from Meyerson that gave him the Nobel Prize. So I will stop there. Any questions before we call it quits for the day?
Yes, I do have a general question. So when you were pointing on the graph, I couldn't see your mouth or pointer. Is that just a problem that I had, or is it due to the presenting mode?
I'm sure it's the general problem, I bet. Did other people see my mouse? I had the same issue. Okay, so everybody had the same issue. So I apologize. It's the first time I used this, and I could see it on my screen, so I assumed that you could see it too. So I apologize for that. So I think that what will happen on Monday is, oh, actually, so I can point at things and you can see my hand. And so I'll figure out, there's probably some solution, but I don't know what it is, but I'll try to figure it out over the weekend. So that was a very good question. It's also a good example that, probably if you do have a question like that, probably everybody else has the same question. And so it's definitely worth raising. So I appreciate that. Anything else? Okay, well, let's break. You guys have a wonderful weekend. I know it's Friday evening now for you, so so enjoy, but do stay safe. And I'll see you on Monday. Good, thank you very much.